Okay, so covalent bonds. So when we're talking about covalent bonds, you guys are already aware that we have these lone pairs. Lone pairs are the electrons, the valence electrons that are not going to be involved in bonding. Okay. And you guys also know about the octet rule, right? So we want to try to obey the octet rule. In most cases, there are going to be exceptions, okay, where we disobey the octet rule. So which elements are going to be able to disobey the octet rule? You guys remember? Okay, hydrogen, because we know that hydrogen can only have two around it. What is the other one?
B, and F.
So sulfur, and I believe phosphorus. Is that right? Let me pull up a periodic table. That might help us. Can you guys see my periodic table? Okay, so any of the nonmetals that are in the third period and higher. So bromine, iodine, and even some of the noble gases, right? They're going to be able to sit there and disobey the octet rule because they have the d orbital to put electrons in. Does that make sense? Okay, I assume so, since nobody said anything. Okay, we talked about polar and nonpolar. So when we're talking about covalent bonds, it could either be a polar covalent bond or it's going to be a nonpolar covalent bond. A polar covalent bond basically means that you have a negative pole and a positive pole. So it's kind of like bipolar. One's positive, one negative, right? You guys know what bipolar means for people?
Yeah.
What does it mean for people?
They have different mood swings.
Speak up just a little bit louder. So if someone is said to be bipolar, what do you think that means?
They have mood swings.
They have mood swings, right? So they go from really happy to really sad, right? So really positive to really negative, okay? So something is bipolar. So in this case, we're talking about a compound that is bipolar. It has a positive pole and a negative pole. So basically, that basically means that the electrons are going to be shared, but they're going to be shared unevenly. And I'll show you a picture that kind of helps you visualize it. And then what we have is also a non-polar covalent bond. A non-polar covalent bond is when we're sharing evenly. Okay, so that means that the electron is spinning equal amount of times on both sides. Okay, so in the first example, this is an example of a non-polar covalent bond. So they're being shared evenly, right? So X and Y are getting the electrons the same amount of time. I mean, X and X, same amount of time. In the case of a polar covalent bond, then this X is getting the electron less than the Y. So it's spending more time on the Y side. And then an ionic bond is when we just get the transfer, when you just give up the electron entirely, right? So one doesn't have an electron and one does. One is giving up an electron. Does that make sense?
Yes.
Okay, so we've talked about electronegativity. We know the trends of electronegativity, right? So we know that if we're on the metal side of things, like the alkali metals, those guys are going to be low in electronegativity. In other words, they're not going to want to attract an electron. Where if we go over to fluorine, fluorine is going to have the highest electronegativity because it wants an electron really, really badly because it's only one away. So if you guys look, this is just a diagram of that electronegativity. So you can see here we have fluorine has the highest electronegativity, where francium has the lowest, right here. Okay, the way that we use that electronegativity is we calculate that difference. And I talked to you guys about that in lab. So if that difference is between 0.5 to 1.8, we know that that's going to be polar, right? If it's less than 0.5, we know that that's going to be nonpolar. And then if it's greater than 1.8, we know that that's going to have ionic character. Okay, so when we take a look at hydrogen and oxygen. So oxygen is 3.4, hydrogen is 1.2. We subtract the difference, then it's 1.2. That's wrong, sorry. That should be 2.2. Okay, if we have hydrogen and carbon, well, carbon is 1.6 and hydrogen is 2.2. So the difference is 0.4. So is that going to be polar or non-polar?
Non-polar?
It's going to be non-polar. So we know that in the case of methane, the bond between the hydrogen and the carbons, each of those bonds are going to be non-polar. Okay, where in the case of water, you know that these guys, the bonds between these two are going to be polar. Okay. So we've talked about triple bonds. So how many electrons are shared in a triple bond?
6.
6. And a double bond, how many?
4.
And then a single bond. Okay, you guys are all familiar with that. We've talked about how to do Lewis dot structures, right? So in the case of who's going to be in the center? let's say we have the ammonium ion. Who's going to be in the center in the case of the ammonium ion? This NH4 plus. So how many, well, first off, how many valence electrons do we have totally with NH4 plus?
Nine.
Okay, so each of the hydrogens you said has one. So 1 times 4.
4.
Okay, so that's 4. And then the nitrogen has how many?
5.
What does that plus mean?
You're gonna take away.
Say it again.
You're taking away an electron.
I'm taking away electrons. So if this is 9, now I'm subtracting one of them. So minus 1. So then that's 8. So I have 8 electrons to work with. So who's going to be in the middle?
8.
Which one? Who's going to be my center atom?
Nitrogen.
Thank you. Okay, so that's 1, 2, 3, 4. And then we have hydrogens, 4 hydrogens surrounding it. Can hydrogen ever be in the middle?
No.
Why not?
It's the kid that throws up.
Is this the kid that throws up? Yes, it always has to be at the end because it can only form one bond. Okay, piece of cake. And then with ions, we always want to put the bracket around them to let us know that there's a charge associated with it. And we put that charge on the outside. Okay. Questions, concerns, cash, credit. Okay, we're moving on. So there are exceptions to the octet rule. One of the exceptions is if you have a total odd number of valence electrons. So how many electrons does valence electrons does nitrogen have?
5.
Okay, so nitrogen has 5, and how many does oxygen have?
6.
6. So if we add these guys together for nitrogen monoxide, that's a total of 11 electrons. Now, if you can make it reach its octet, I will give you $100. Can you do it? Can you make it so this compound could ever reach its octet without
No.
adding or removing an electron?
No.
You can't, right? So you'll never get my $100. Okay, so it's an odd number. Anytime that you have an odd number, you should immediately know for the total number of valence electrons, if it's an odd number, you should immediately know that one of them is going to be deficient, right? One of them is not going to be able to reach its octet. And the way that we decide who does not reach its octet is based upon electronegativity. The one that has the greatest electronegativity will reach its octet, the other guy won't. Okay, so in this case, oxygen reaches its octet, that's 2, that's 4, that's 6, that's 8 around oxygen, and where we have 7 around nitrogen. And you're going to try to get it as close to the octet as possible. So that's why we get it to 7. We don't just leave it at 5. Are you with me?
Yes.
Okay. And that's the same thing here in the case of NO2, right? Nitrogen dioxide. Okay, another exception is molecules that have more than 8 pairs of electrons around them, or have more than 8 attachments, right? So in the case of phosphorus, in this case, we have 2, 4, 6, 8, 10. We have 10 around there instead of having just the 8, right? So again, these are the guys that are going to be in period 3 or higher, right? So if you're in period 3 and higher, you have the potential. It doesn't mean you will, but you have the potential of breaking the octet rule because you can use that d orbital. Okay, are you guys? I mean, sorry, d subshell. Okay, and the same thing with sulfur. Sulfur is going to be able to do it as well. So this guy is called hypervalence, as in hyperactive, hyper. Valence. Okay. You have hypovalence. So molecules that don't like to reach their octet. So in the case of beryllium and boron, these two guys, beryllium, although it's considered to be a metal, it will actually act like a non-metal, and it won't reach its octet when it forms bonds. It only likes to have 4 electrons around it. We have boron. Boron only likes to have 6 electrons around it. So these guys are called hypovalent. Or hypovalence. And occasionally we'll have incidents with oxygen. Because we form these polyatomic ions, sometimes they will cause other things to sit there and break the rules. Oxygen won't, but other things will. Okay, so we've talked about ionic bonds, we've talked about covalent bonds, we have polar and nonpolar covalent bonds, and now we're going to talk about metallic bonds. Metallic bonds are bonds between metals. So how many of you guys have gold chains? Any of you guys have gold chains or gold rings or gold earrings? Angel, do you have gold earrings?
No.
No? Do you have any gold at all?
Yeah, my cape.
You said your cape is gold?
My chain.
Okay. So is it 24 karat gold? Or is it 18 karat gold? Or is it 14 karat gold? Or is it just gold plated?
14.
14 karat gold. Good. Okay. So if it was 24 karat gold, that's pure gold, right? 18 and less, that has other metals in it. Those guys we call alloys because they have other types of metals in them, right? Based upon the percentage of gold that you have in there, that carat goes up, right? 24 karat gold, 100%. At 18 karat gold, I'll show you here what it is in a second. And then 14 karat gold, it'll be less than that, so on and so forth. But there are other metals that are going to be replacing some of the gold in that metal. Now, those guys form what we call an alloy. An alloy is an example of a metallic bond. Now, in the case of metallic bonds, what happens is, because we know that the metals like to get rid of their electron. You guys notice that? They're always going to end up being pluses. Have you noticed that so far? Okay, so since they like getting rid of their metals, what they do is, let's say we have sodium metal. We know that sodium has one valence electron, right? So what sodium does, it'll actually drop that one electron next to itself, make itself a plus. So this is my sodium now, and then this is that electron that he puts next to him. So he like drops it right next to himself, and like it doesn't belong to him. So then the next sodium does the same thing. And then drops the electron next to itself. And then the next sodium does the same thing. And then the next sodium does the same thing. And the next sodium does the same thing. So then it pretends like, okay, so I'm sodium, I'm plus, but my electron is minus. I'm sodium, I'm plus, my electron is minus. Now this process is called delocalization of the electron, or delocalized electron. So they delocalize their electrons and act as if they're independent, like it's an independent atom that's interacting with it. Kind of like what you would do with fluoride ion and then the sodium ion, that alternating. Does that make sense? Maybe it'll help if I show you the real picture, right? So here's an example. This is an example of like sodium. Sodium is going to be plus. Here's that electron. This is sodium. This is sodium plus. This is its electron. So it literally just drops those electrons. And these electrons are kind of like the C electrons. They kind of orient themselves to act as if they're alternating with that sodium ion. Okay. So this would be the case for like magnesium. It drops 2 electrons and it pretends like it's 2 plus. Okay. Now, the way alloys are formed is that you basically put in metals that are almost the same size, that have the same charge, and they'll do exactly the same thing with that metal. And so we're able to sit there and form alloys. And the benefit of forming alloys, instead of having all the pure stuff, is one thing, it could be cheaper in the case of gold, right? So we know that 24 gold is more expensive than 18 karat gold, which is less expensive, which is more expensive than 14 karat gold, and so on and so forth, right? Or it can reinforce things, make it stronger, right? So by putting those things in there, you could actually make something stronger. So like, for instance, stainless steel. Stainless steel is a combination of steel and this is a combination of iron and I think it's chromium. And so it has so much iron and it has so much chromium and probably some other metals in there too, that it doesn't rust, right? So we know that stainless steel doesn't rust. The reason why it doesn't rust is because you have those other metals in that alloy other than iron. If we had pure iron, it's going to rust. Okay. So these are examples of some of those alloys that I was talking about. So like, for instance, 18 karat gold. We have 75% gold, 12.5% silver, 12.5% copper. Brass is going to be about 60 to 95% copper, and then 5 to 40% zinc. That's stainless steel that I was talking to you about. Stainless steel, 70% iron, 18 to 20% chromium, 8 to 12% nickel. Okay, so there are benefits to using alloys. One thing is cost, the other thing is it can make it better. That alloy can make it better. If we just had pure iron, it's going to rust on us, So we're not going to make a bridge out of pure iron where it rains all the time. Does that make sense? Because we know that water causes iron to rust, right? So would it make sense to sit there and use pure iron for a bridge somewhere where it's constantly raining? Yeah, no? Let's see. Priscilla. Does it make sense to build a bridge somewhere where it's constantly raining of pure iron? Are you guys there?
Yes, sir. Yeah.
Yeah, you guys are there. So does it make sense? Would you build something of pure iron? Would you, first off, would you build anything above water with pure iron?
No.
No, because we know it rusts, right? And so you want to take that into consideration when you're designing something or building something. Right? If any of you guys are planning to be engineers, this is one of the things that you want to take into consideration. Would you make pipes of pure iron? If you're going to go into agriculture, you have this choice of buying these really cheap ass pipes for like 50 bucks, but they're all pure iron. Or you can get the ones that are, 75 bucks that are stainless steel. What would you do?
Stainless steel one.
Stainless steel, right? Because if you buy the ones that were pure iron, they're going to rust at some point, right? And you're going to rust a hole in it, and then you're going to have water going everywhere, right? So you want to take those things in consideration. Are you guys with me so far? So at this point, you guys should all be competent at doing Lewis dot structures or Lewis diagrams. Are you competent?
Yes.
Good. Okay, so if you're not, these are just kind of some of the instructions on going through that process. I'm not going to go over them. You can read them. You guys have the notes in front of you. You should be able to sit there and decipher it. If you do have any questions, I am more than happy to help you, but you got to come off with questions yourselves. Okay, so we'll start off with this. Draw the Lewis diagram for ammonia, NH3. Also, I should also add, you should be able to identify ammonium and ammonia. Okay, they're different from each other. Ammonium is NH4 plus, ammonia is NH3, and you should also know what water is. Okay, so where am I going to start?
With the valence electron.
Okay, so I'm going to start at, you said, who's going to be in the middle? N is going to be in the middle. How many valence electrons does N have?
5.
5. Okay. How many valence electrons does each of the hydrogens have?
1.
So what is my ultimate goal? What am I trying to do with the Lewis structure?
Fulfill the octet rule for each element.
Fulfill the octet rule for each element. Okay, so how am I going to do that? I have a total of 2, 4, 6, 8 electrons to work with. So what am I going to do? So obviously you guys already told me I put N in the middle, and then a bond. So that's going to bond with H.
The hydrogen bond.
A bond between nitrogen and hydrogen again.
Mhm.
Is that right?
You have to add 2 electrons to the nitrogen.
Have to add 2 electrons to the nitrogen. Okay, so then I have 8 electrons that I've worked with. So that's 2, 4, 6, 8. So I have 8, right?
I said stop. Move.
So how many do I have around the nitrogen?
8.
How many do I have around each of the hydrogens?
2.
2.
Are we done?
No.
No, we're not done?
That looks right.
That is correct. This is done. Okay. What about this guy? This, it says, draw the Lewis diagram for the hydrogen carbonate ion. No yawning, it's too early. Okay, how many total electrons do we have to work with? Valence electrons do we have to work with?
24.
So 24? Okay, so we know that there's 1 with hydrogen. We have how many with carbon?
4.
And how many with each oxygen? We have 3 of those. Okay, so 3 times 6, 18, my age. And that minus means what?
You have 1 extra electron.
So we have 1 electron. Okay, so I add these together. 1 plus 18 plus 1 plus 4, so I believe that's 24 total electrons. Okay, who's going to be my center atom?
Carbon.
Carbon. Carbon has how many again? You said 4, if I remember correctly. Okay, and so then what am I going to put around carbon?
Oxygen.
Okay, oxygens. And oxygen has how many again? 6. Ugh. And then the hydrogen. Okay, so I need to maneuver this around so that everybody reaches this octet. So what do I need to do to make that happen?
Add single bonds.
Add single bonds, okay. So I have a single bond here. 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 Okay, so that means I have to get rid of a couple of electrons because they're sharing, right? That's what that line represented. Okay, does that work? Okay, let's find out. Let's do the math here. Okay, let's start off with this bond right here up top with the hydrogen. This one right here. You guys see it? So is hydrogen happy?
Yeah.
Okay. What about around the carbon? Is carbon happy?
Yes.
2, 4, 6, 8. Okay, what about this oxygen here? Is it happy? No, it's not happy. Okay, this oxygen, it's not happy because we have 2, 4, 6, 7. 2, 4, 6, 7. 2, 4, 6, 7. I'm sorry. Yeah, 2, 4, 6, 7. So none of those oxygens are happy. So what do we need to do to fix that? Any suggestions?
A double bond.
A double bond. Okay. So say we put a double bond here. So we're taking, and we're gonna. Right from here. Okay, so that's 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 20. Wait, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25. So that's too many. If I get rid of this, I have too many now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so I have 24 electrons, which is what I said I had. Now, what else do I need to do?
Brackets and a negative superscript.
A negative superscript. Is the octet rule satisfied for everyone? 2, 4, 6, 8, 10. Is the octet rule satisfied for everyone?
No.
No.
No. Okay, so this guy's octet rule is satisfied. But this guy has 10 around it. This guy has 8 around it, but this guy only has 6 around it. So neither carbon nor this oxygen are satisfied. Okay. So what if we did something like this? Yeah. Okay, we did something like this. Two, 4, 6, 8, 10, 12, 14, 16, 18, and so on. Oops. 18, 20, 22, 24. It's way too many. So if we did something like this, okay, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Does that work? And that's 2, 4, 6, 8 around this oxygen. That's 2, 4, 6, 8 around this carbon. That's 2, 4, 6, 8 around this oxygen. That's 2, 4, 6, 8 around this oxygen. And that's 2 around that hydrogen. Does that work better compared to this? So this is an option. What about this guy? That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's 8 around here, 8 around here, 8 around here, 8 around here, and 2 around here. So does that work? Yes, no, maybe?
Yeah.
Okay, so under the circumstances, both of these guys work. So these guys here, and technically I have a third possibility, I have this guy. Put it in a different color. Where we have a double bond on this oxygen. Okay, so same concept, just switching the oxygen. So these guys, these two here, these guys are considered resonant structures. So resonant structures are basically when the electrons are moving between two identical elements, right? So in other words, you have a double bond here, the other time you have a double bond here. We have a double bond here in this case, but now we have a double bond here. These guys are exactly the same molecule. They're the same thing. Only thing that's different between them is where that double bond is located at, right? That is considered a resonant structure. Where these guys, this guy and this guy is considered to be an isomer, right? So you have a double bond on the OH over here. That makes this a different structure than this guy. They're going to behave differently in terms of their chemical properties because of that double bond being over here with that OH part. So these guys are resonant structures. These guys are isomers. Same chemical formula, but different chemical structure. Are you with me? Everybody got that? Hands up. Everybody got it?
Yes.
Okay. Good. Okay, let me clear. Okay, so we just talked about resonant structures. So they're going to be basically equal structures from each other, right? The only thing that's changing is the position of the electrons. We also talked about isomers. So here is an example of resonant structures. So you have the double bond on this oxygen. In this case, you have the double bond on the oxygen that's going down. Here you have the double bond on the oxygen that's going to the left, right? And so they're the same chemical structure. They're just, the electrons are in different positions at different points. Okay. Okay. So we talked about electron pair geometry. So the valence shell electron pair repulsion theory, VESPER. That basically means that we're taking into account that the electrons are going to repel each other, right? And so that plays a part in it. That's going to affect our angles, okay? So we've talked about it that a lot of the elements try to make a tetrahedron or a tetrahedral compound. So if we take a look at, let's say this ball with sticks, right? So if it's linear, right, that means that you have a 180 degrees. You have an electron pair here, an electron pair here. So basically the electrons are going to want to be as far away from each other as possible, right? The farthest away that you can get is 180 if you have two pairs of lone pair electrons, one here and one there. Okay, so they're going to try to get as far away as possible. If we have three pairs of lone pair electrons, they're going to be 120 away from each other, right? Because that's the furthest that they can get away from each other. And then if we have four pair of lone pair electrons, then that angle is going to be 109.5 because that is the furthest they can be from each other. Okay, are you guys there? Okay. Here's just the same concept with balloons. So if I have two things that are connected, it's going to form a linear structure. If I have the two balloons together, it's going to be a 180 bond. It's going to be linear. If I have three balloons connected, it's going to be trigonal planar. Each angle is going to be 120. If we have four balloons that are tied together at the center, then this guy is going to be tetrahedral. It's going to be 109.5 between each of the angles. This here is that nice little table that you guys, I believe, have in your packet. You guys have it in your packet, yes or no?
Yeah.
Okay. Okay, it helps us understand that whole concept. So if I have a center atom and I have two atoms attached at each end, this guy is going to be linear. Two attachments. If I have three attachments, it's going to be trigonal planar. In this case, I have three attachments, including that lone pair. So two of them are going to be atoms, one of them are going to be a lone pair. This guy, the electron pair geometry is going to be trigonal planar, but its molecular geometry is going to be bent. So you guys see it here, that bent structure. If I have four things attached and all four things are like atoms, this guy is going to be tetrahedral. So the electron pair geometry is going to be tetrahedral and the molecular geometry is going to be tetrahedral. If I have four things attached and I have one of those attachments being lone pair, the electron pair geometry is going to be tetrahedral, but the molecular geometry is going to be trigonal planar. If I have four things attached, two of them being lone pairs and two of them being other atoms, then this guy's electron pair geometry would be tetrahedral since it has four attachments. But since these guys are lone pairs, the molecular geometry is going to be bent or angular, like in the case of water. Okay, how are you doing so far? Okay, so here's an example. Methane is an example of tetrahedral. You have carbon in the center, you have hydrogen, 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 hydrogen. So these guys are going to be equally distant apart from each other. This guy is tetrahedral. This guy, in the case of ammonia, we have a lone pair up top. That lone pair is going to be kind of pushing things down. So it's going to make that thing seem like it's trigonal planar, but it's going to be pushing it down. The lone pairs. In this case, you form like a little pyramid. So this guy is going to be called trigonal pyramidal, or its molecular geometry. So what was the question? Are you guys there? Okay. So in the case where we have two sets of lone pairs, 1, 2, this guy, you're going to see it as being bent because you don't see those lone pairs as an attachment. So it looks bent to us. Okay. Okay, so the next thing I want to talk about is drawing the wedge dash diagram. So the wedge dash diagram helps us understand that three-dimensional aspect of things. So the wedge means things that are going to be moving towards us. The dash means it's moving away from us. Okay, so Okay, so in this case, this is the wedge dash diagram. So in this case, this chlorine that has this wedge, this guy is going to be coming out towards us, right? The Cl with the Wi-Fi signal looking thing, that is your dash. That dash is going to be going towards the back. So it's like one is coming towards us, one is in back, okay? And then this guy that has just a line, that's in plane. That's in the same plane as that atom. So you have an atom, one that's one atom, or the central atom. You have the one that's in the same plane as the central atom. You have one that's coming forward and one that's coming back. Are you with me?
Kind of.
Okay. So when you guys remember, you were doing a 3D structure, right? So you always have like, when you guys were doing the molecules, right? So if we're doing, and you guys did this with me, I believe. So if we're talking about methane, the way that we would draw methane is we'd have our carbon in the center. We have up top in the same plane lined up with that carbon, we're going to have a hydrogen. We're also going to have another one. We have one coming towards us. One coming towards us. So that's going to be wedge. And then one that's going in the back of it. So remember, it's like that jack. It gives us that 3D structure. Sorry, my wedge sucks. My dash sucks. Okay. So the dash represents that back. One is coming out towards you, and one is right next to you, and one is right above you. Just like the jack.
Okay, that makes sense.
Okay. Okay, so let's see here. Okay, so we've talked about the bonds and how to determine how many attachments that we have and all of that stuff. So when we have double bonds play a role in it to some extent, but it kind of minimizes it. A double bond doesn't truly affect the geometry. It just lets us know how many attachments that we actually have. What do I mean by that? So if we have this molecule would be, if we do the Lewis dot structure for this guy, we know it's carbon has 4 valence electrons. Each of the carbons do. So, and then I have 2 fluorines. Fluorine has how many valence electrons?
7.
We know who's going to be in the middle, carbon or fluorine.
Carbon.
Carbon.
Okay, so how can I set it up so that everybody has their octet filled?
Here's 2, here's 2.
Single bonds.
Bond.
Okay, so if I have single bonds with the fluorines and the carbon, Okay,
Can you make the bond between the carbons a double bond?
a double bond. Okay. So then I get rid of these guys. Okay, so that's 8 around this fluorine, 8 around this fluorine, 8 around this carbon, 8 around this carbon, 8 around this fluorine, 8 around that fluorine. Okay, so what would be the molecular geometry of this half of that compound? How many attachments do we have on that carbon?
2.
Not how many bonds, but how many attachments?
Oh, 4.
Attachments, things that are physically attached to it. Different things that
2.
are attached to it.
Or 3.
3. Yep, 1, 2, 3. So that's 3 things attached to it. So what would be the molecular geometry of something that has 3 things attached?
Trigonal
Trigonal what?
planar?
Trigonal planar. Okay. And what about the other carbon? This one here?
Same thing.
Same thing. So both of these are going to be trigonal planar. Okay, simple. So if I was drawing a wedge dash for this, you could either draw it all in the same plane. It would be the same thing, which is what we have here. They're all in the same plane, the way it is. Or we could sit there and draw it like this guy is in front. This guy is front. This guy is back. And same thing over here, where you have one in front. One in back.
Does it matter where the pointy part is pointing at for the wedges?
It does. You always want it pointing towards the center atom.
Okay.
I know my pointing part sucks for my dashes, right? And also for the wedges. See? So if you look here, it's always pointing towards that center atom.
Okay, thank you.
Okay. Okay, so wedge dash, wedge dash, wedge dash. Okay, so then we are at molecular polarity. Okay, so when we're talking about molecular polarity, we're taking into account both the bond angles and then the polarity of the entire thing as the sum, the whole thing. Okay, so the guy that's going to be more electronegative, that means that things are going to be going more towards it. Okay, so here we're going to be looking at these molecules. We're going to be looking at CCl4, and methane, and then we're going to be looking at things that are going to be in between. So these guys here, these molecules are not going to be considered symmetrical, where these guys are going to be considered symmetrical. Okay, so let me explain to you why these guys aren't symmetrical. Okay, so this is that CCl4. So if we have CCl4, we have a chlorine here, chlorine here, chlorine here, and chlorine here. This is carbon in the middle. So if we looked at the bonds independently, this guy is going to be, the carbon is going to be partially positive. The chlorine is going to be partially negative. So the electrons are moving towards the chlorine in each cases, in each of these cases. Right? So we have this going on. Right? So it's kind of like you have these quadruplets that are all about the same strength, pulling at you on your leg, your arm, and your other leg in equal force. So nobody pulls you towards them. Okay, so in that case, there's no net dipole moment, meaning that the electrons are not going more towards another. Okay. So in the case of, but these guys are considered to have symmetry. So if we cut along the axes, it's going to be exactly the same in all directions. That guy would be symmetric. Okay, so we have this guy. In this situation, we have the electrons being pulled towards this way. We have the electron being pulled towards this way, the electron being pulled towards this way. And so overall, and then this electron here is going to be pulling towards this guy because these guys are pulling. So there's no pull, there's no dipole moment in this direction at all. This guy's partially positive. All of these guys are partially negative. The overall movement is going to be between the two axes. So you guys see it here. So it's going to be between these 3 points. So if we add our structure, here's our center. It's going to be to the side where that are more electronegative, right? So it's going to be between all 3 of those, right? So in this case, this guy is non-symmetrical because we can't find an axis where it's exactly the same. Okay, so in this case, we have hydrogen, hydrogen, chlorine, chlorine. Chlorines are very electronegative, so then it's going to be pulling between the 2 chlorines, the electron is. So it's going to have a dipole moment. You're going to have a net dipole moment. And as a result of that, that guy's going to be polar. That molecule is going to be polar. This guy also does not have symmetry, right? Because on one side we have symmetry, but the other way we don't. This guy, right? It's going to only be pulling towards this way because chlorine is stronger than all of the hydrogens. So the electron is going to be pulled more towards that chlorine than each of the hydrogens. Okay, so does this guy have symmetry or it does not have symmetry?
It doesn't.
It does not have symmetry. And then our last case where we have all hydrogens, since you have equal pulling in all direction, it's going to cancel each other out. There's going to be no dipole moment. Okay, do you guys understand that?
Yes.
Okay, so here's another example of that molecular polarity again. So here we have carbon dioxide. So since these guys, carbon is in the middle, oxygen is on both sides, you have the electron being pulled in this direction. And then you have the electron being pulled in this direction. These guys are equal to each other. So then you're going to have equal pullment going in both directions. So this molecule, since it's being pulled both away from it, it's going to kind of cancel each other out. So there's not going to be a net dipole moment. So this guy would be considered non-polar. So this is non-polar. Where in the case of water, the dipole moment is all going towards oxygen. So then the net dipole moment is going in this direction towards oxygen. So this guy is considered to be polar. Okay, questions, concerns, cash, credit, Kool-Aid? Okay, so the next thing that we're going to be talking about is organic chemistry. Okay, so organic chemistry is defined, and I'm going to give you the very basic general definition. And then there's going to be some modifications that we're going to make to it. Organic chemistry is compounds that basically have carbon in them. Okay, organic chemistry are just study and the research and application of carbon-based compounds. Okay, so if it has carbon in it, it's gonna be considered to be organic. Okay, so carbon, we talked about, carbon is able to have 4 attachments, right? It can attach to 4 different things. Carbon is the center of life. We use carbon quite a bit. It can have 4 bonds attached to it. It's kind of flexible, right? Because it's trying to make everybody happy, right? So we said carbon's a little bit of a whore. Okay, inorganic chemistry are all of the chemicals that aren't carbon-based, okay? Except there are a couple of them that inorganic chemists want to try to claim as not being organic. That's going to be your carbonates. Those are going to be your cyanides. They're going to be the oxides of carbon. And then there's going to be a few other things that are special cases, right? So those are going to be kind of like those exceptions. So carbonates are not considered to be organic, okay? But other than that, everything else that has carbon in it is considered organic. So when you guys were taught organic, you guys are saying, oh, it's natural, it's fresh, it's no pesticides and stuff like that. That's not what it means. It basically means that anything that has carbon in it is organic. So pesticides are organic, right? Because a lot of them are carbon-based pesticides. They have carbons in it. The first thing that we're going to talk about are hydrocarbons. Okay, now I want you to think about this. Think really, really hard. That term, hydrocarbons. Hydrocarbons are made up of only hydrogen and carbon. Does that make sense?
Yes.
Okay, now I want you to think. I'm going to put a couple things on the board, and I want you to tell me if it's a hydrocarbon. Okay. This first one, call this guy A. Is A a hydrocarbon?
No.
Is it organic?
Yes.
Okay. B. Is B hydrocarbons?
No.
Okay. Is it organic?
Yes.
Okay. If we talk to an inorganic chemist, is it organic? What is this guy called? Does anybody know? So if you guys do me a favor, go to page, your periodic table packet. If you guys go to I think it's the 3rd page of your periodic table packet, or the 5th page, let's say polyatomic ions, do me a favor, go there and take a look at that. Tell me if you see CO3 2-. Carbonate. So what did we say about carbonates?
It's an exception.
So it's considered to be inorganic. What about C?
Yeah.
So is that a hydrocarbon?
Yeah.
It's a hydrocarbon. Is it organic? Is it organic?
Yes, I want.
Yeah.
Yes. So yes, it is organic. Okay, so now let's talk about alkanes. So alkanes are just hydrocarbons that are totally saturated. That basically means that they on the carbons are all going to have single bonds attaching everything. So for instance, the one that we just had up, it was C, what was it, C6?
Get your robotic self back over there.
Okay, so each of the carbons have 4 attachments around them. This guy here, these are all single bonds. So alkanes are carbons or hydrocarbons that only have single bonds. There are no double bonds, there are no triple bonds. So these guys are alkyl alkanes. Alkenes these guys are hydrocarbons that have at least 1 double bond. How many of you guys are taking notes by hand? Okay, so alkenes are where you have at least 1 double bond. Okay, that makes an alkene, that E-N-E. Alkanes, all single bonds. Alkenes, at least 1 double bond. Then we have what we call alkynes. Alkynes have at least 1 triple bond.
Do all of them have 4 attachments?
Yes, well, not all of them have 4 attachments. It has at least 4 type bonds. So it'll be a triple bond and 1 bond. So that's 1, 2, 3, 4. So they have a total of 8 electrons around them. So if we take a look at this molecule, right? The one that I'm drawing it. Okay, so if we take a look at this molecule, we have 1, 2 attachments around that C. So what would be the molecular geometry of this very first carbon? It has 2 attachments. Is it going to be linear? Is it going to be trigonal planar? Is it going to be tetrahedral? Is it going to be trigonal pyramidal? Is it going to be bent? Is it going to be, what is it going to be? Linear, that's right. So this first one is going to be linear. Second one, we have 1, hold on. Okay, second one also has 2 attachments. It's also going to be linear. Okay, are you guys there? Can you hear me? Yeah.
Yes.
So if you take a look at this, alkanes, only single bonds. Alkene, E-N-E, it has a double bond. Alkyne, it has at least 1 triple bond. And that makes sense if you think about it. A is at the beginning of the alphabet, E is in the middle of the alphabet, and Y is at the end of the alphabet, right? So it's kind of like increasing order, right? So single, A and E. Double, E and E. Triple, Y and E. Are you with me? Okay, so we are going to stop here.